Hello everyone, welcome to Class 1 of FSE 355 Fire Dynamics Online. This will be a brief introduction into the course, a description of myself, who will be the main lecturer, but there will be guest lecturers as well. And then we'll get into a little bit of why we want to study fire science in general. So a little bit about myself, my education background. I have a Bachelor of Science in Aerospace Engineering from the University of Tennessee, a Master's in Fire Protection Engineering from Worcester Polytechnic Institute, where my thesis focused on measuring fire flow velocity and temperature using cross-correlation velocimetry, which is a statistical sensor technique using thermocouples. And my PhD is also from Worcester Polytech, and my dissertation involved the use of a new instrument I built called a hybrid flame analyzer, where I was looking at the effects of pulverized coal on the burning velocity of methane air flames. So turbulent methane air flames, what happens when you throw coal dust into them. And this is relevant when you're dealing with coal mine explosions, because they often start with a methane gas pocket, and then that ignites and then trains coal as it propagates through the gallery. So that's what my research focused on. My teaching philosophy, I like to make the course entertaining, challenging, and applicable. So we don't want it to be boring. That's no good. And it can't be too easy, because if it's too easy, then why take the class in the first place? But it needs to be applicable. This is a big one. It needs to be usable in real life. So all of the concepts that I don't think are important, I'll either just leave them out or graze over them. And if you want to go into them in more depth, you're welcome to do so. And if you have questions, you can always ask me. But I'm going to focus on the things that I think are most important and will be most useful for you as the students. I am looking for class participation. We're going to have discussion boards and several other ways you will participate with each other. So hopefully you'll build relationships with your classmates and be able to use those in the future. All right, so my dissertation, I said it was on measuring the burning velocity of things, and so I made some interesting videos along the way. I like to use a lot of videos in my lectures, so kind of try to keep the students' attention. And so we have a few here. There's a few different ways to measure burning velocity. You can use something like this, where you take a long tube and fill it with a flammable mixture and ignite it at one end and measure how long it takes for the flame to propagate from one end to the other. And that's a reasonable way to do it. It's hard to control this flame shape, but you can do what you can do. You can also take a balloon, fill it with a flammable mixture, let it spark in the middle, and watch the flame front propagate out. This is a balloon filled with methane and oxygen and recorded at 5,000 frames per second using a very nice camera that they let me borrow for a day. And that's a constant pressure flash fire. You can also do a constant volume fire or explosion, where you have a flammable mixture inside of a closed container, and then you ignite it and watch the pressure wave rise inside of the container. So this is a box that actually has a burst disc, and so we can see the box expand and then the burst disc pop. So if we were measuring the pressure inside of this, we could relate that pressure to a burning velocity somehow. And then we can also look at the flame shape. So the shape of the flame is on an anchored burner is going to be related to the burning velocity. So I'm not going to get into how all that works, but that was what my dissertation was about, and I thought the videos were interesting, so I would include them here. Alright, so the course design. We want to talk about the course design. I'm sure you're quite interested. We're going to have 2 lectures per week. This is similar to the on-campus course, not the online course, the on-campus course. We're trying to make them similar. We're not saying that the two, if you take the class on campus and the class online, are exactly the same, but we're trying to make them similar as we go forward and we get closer to ABET accreditation that we're working on right now. We're going to turn in notes for each lecture. You're going to turn in notes for each lecture. So on Blackboard, you will find an outline set of notes for each class. And so as you watch the video, you're going to go through and fill these in, and then submit those lecture notes as your class participation for the day. So that way I feel like when you're on campus, you get credit for being in class. You have to be in class. So I feel like if you're going to take an online course, you should get some sort of credit for actually watching the video and taking notes. And it's been shown that taking notes benefits the learning process in literature. If you look into teaching literature, the process of actually taking notes is useful, and I've taken a number of online courses myself where you just sat there and watched the video and spaced out half the time, so we want to try and limit the amount of spacing out that you do. Inside the lecture, there's going to be these 5-minute in-class activities. Now, I run in-class activities on campus courses, and so for you guys that are online, for you people, I apologize if I say you guys. I don't mean it to be anything offensive, but for the on-campus students, they have these in-class activities that they do to reinforce the concepts that we cover in class. So we're going to do a similar thing for the online lectures. And similar to the on-campus courses, once again, we're going to have virtual laboratories. So the on-campus courses use real laboratory experiments, but since you guys probably don't have access to a combustion lab or a fire lab or a burn building or a wide open space where you can go outside and burn stuff without risk of hurting or the fire spreading, hurting people or the fire spreading, we're going to do virtual laboratories. So we've recorded a whole bunch of fire experiments, and you're going to watch them and analyze the data that comes back, getting it as close to a real-life burning experience as we can. And I think there's a benefit in doing a virtual laboratory, and once I'll probably actually start to use these in the on-campus courses as well, because real experiments take a lot of time, a lot of money, and a lot of effort to set up. So you can only set up 2 or 3 per semester, whereas opposed if you do virtual laboratory experiments, you can do a significant number of sort of virtual experiments where you let the student go and watch the video, and it doesn't take nearly as much setup time, or the setup time you only have to do it once, and you can let a lot of different students use it. So I think there is a benefit for both the on-campus and the online students for doing these virtual laboratories. We are going to do a lot of modeling in this course. We're going to basically cover the fire dynamics book. In the first half of the course, it should be a review for the first month. Let's say the first few weeks, we're going to go over the concepts you learned in FSE 120, but go into them in a little more depth than you would have done in 120. And then use those fundamental concepts in modeling for the second 2/3 of the course. Now, the modeling will be easier if you have a PC. I own both a Mac and a PC. If you're a Mac person, then that's fine, but it is more difficult. The Mac is not as what's the word? Well, the programs weren't compiled to run on a Mac. So we're going to be using two main programming things, or 2 main modeling programs. You're not actually going to have to program them yourself, which is handy. I might make a fire modeling course later where we do actually program for fire models, but we'll see. But we're going to use CFast, which is a zone model, and it was compiled by NIST and written by NIST. The latest version was anyway, and it was written to run on a Windows-based computer. I do have a recompiled version that was done by Dr. Overholt, and you can use it, but it's very difficult to use, and we'll talk about that when we get there. And then we're going to use these things called FDTS, the Fire Dynamic Tools, written by the Nuclear Regulatory Commission, and they work on the newer versions of the Mac operating system, but the older versions of the Mac operating system don't seem to recognize the macros, so there's a problem there. I am trying to get remote logon access to library computers on campus to online students. I'm not there yet. I haven't done it yet, but possibly that will be an option if you are a purely Mac person. Otherwise, hopefully you can either work through it with your Mac, you can partition your Mac and make a Windows side or run an emulator. If you're an intensely Mac person, you can probably figure out how to get around the compiling issues. All right, so math learning scheme. We are going to do some math in this course. I will teach you what you need to know. I pride myself on my ability to teach people math, so hopefully you will be able to understand what's going on. So to learn the math that we're going to do it in a four-step process. We're going to have in-class examples. I'm going to work the in-class examples for you. I bought a tablet, sort of writing tablet that works with this computer I'm using, so I can work it out on the screen here for you. We're going to do in-class activities. So these 5-minute in-class activities I've been talking about, you're going to watch me do an example, and then you're going to work out an example for yourself and turn that in as part of your class participation. We'll have homework that'll be similar to both the example and the in-class activity. And then the exam and projects will require you to use the homework, the skills you learned in the in-class example, the in-class activity, and the homework. So we have a 4-step problem. These will be word-based problems. Okay, I'm not going to give you x, y equals z, solve for x. Who cares? That's just algebra. This isn't a math course. We're going to use math. We're not going to study math. There's a distinct difference, in my opinion. So we're going to ask questions like you were asked to solve something in real life, and we're going to try to tie these questions to something that would be useful in real life, making it applicable. So we're attempting to show the applicability of the concepts as best that we can. So I'm not going to ask you to solve some abstract two-dimensional problem that has no real-world usefulness like I was asked to do in grad school. And not that I'm bitter. So moving on. All right, so we're going to scan or submit lecture notes. You'll be given partial notes. They'll be in Word form, so if you want to type directly into the Word document, you're welcome to do that. If you want to print it out and write out the notes by hand, you're welcome to do that as well. You'll need to write down the examples yourself or type them out or however you want to do it, and complete the in-class assignments, once again, either by writing them or typing them out, however you see fit. You can work with others if you like for the in-class assignments. That would require some sort of collaboration, watching the lectures at the same time or doing them later. However you want to do it is fine by me. You'll have 5 minutes in the lecture to work the problems. I put in this 5 minutes basically to minimize the activation energy for you to do the in-class activities. In other words, I don't want you to have to stop the lecture, work on something, start the lecture again, and then continue on with your day. I want you to just watch the lecture. You get time in the lecture to work on the problem I give you, and then we get to move on. So there's no stopping, getting distracted, and forgetting to start and get started again. You do want to submit your notes before moving on to the next lecture. And once again, there'll be a place to submit it on Blackboard, and we'll talk about Blackboard here in a few slides. If you're not familiar with that already, if you're taking this as a junior, as an online student, you'd probably be familiar with Blackboard, but we're going to talk about it a little bit anyway. All right, so I'm going to give you, since the equations are not included, the equations in the lecture notes are not included in the outline of the notes, I'm going to give you an equation sheet since there's not one in the book. So we're writing the second edition of the book and right now, and we're going to include an equation sheet and a set of tables. So the equation sheet looks like this, where you have all the variable names, you have a nomenclature here, you have temperature conversions, t-squared, growth rate, geometry, heat flux calculations. Basically all the equations that we're going to use in the class are located on this equation sheet, and you'll have this available to use for you. I'm also going to give you a set of tables, this one. Oh, okay. A set of tables. The tables look like this. It's 4 or 5 pages long. It is basically all of the reference tables from the book. So right now there's not an appendix in the book with all the reference tables in one place. So if you want to look at conversions, you have to go to chapter 2. If you want to look at specific gravity and densities, you have to go to chapter 4. And it gets quite confusing to try to remember where these values are. So I'm giving you a copy of the tables to use for yourself. All right. So we have important concepts. Now, important concepts are the major concepts I want you to learn from my teaching style. They're not the learning objectives for the course. We'll have those specifically in the syllabus. But there's a few important concepts that if there's one thing you remember from this course, or maybe three things or four things that you remember from this course that you fundamentally understand, that would be this. The concept of it depends. Alright, so when you're asked a question about fire, the answer is almost always, it depends. And it is rarely always or never. In other words, concept is a complicated behavior. If someone asks you, does fire burn uphill? You would say it depends. Well, what if there's wind blowing down the hill? Then the fire would spread down. There's almost always a scenario where the rule of thumb or the general behavior of fire doesn't apply. So you want to be aware of this. We'll be talking about it more as the course goes on. And so as long as I'm teaching the course, if you do not understand a problem and you write it depends, I will give you 10% credit. So if the homework problem is worth 10 points and you just have no clue how to do it and you write it depends, I will give you 1 point out of 10. Whoops, I went backwards. Alright, so that's the concept of it depends. It's tied in with the concept of that the answer of always anything or never something is rarely accurate or valid. Alright, so next is the concept of units. We're going to focus on units significantly in this course. Once again, as long as I'm teaching it. The idea being, if you ask me a question and I say the answer is 5, I'm right. Now, you don't know 5 what, but I can always be right as long as I relate 5 to the actual answer. So in this course, you need to write an answer and whatever units you're dealing with. So if it's 5 meters, that's fine. If it's 5 feet, whatever. All right, we will be focusing on scientific units. We're going to use metric units, so meters, centimeters, kilograms, joules, watts. And I will explain all of what these things are as we go through if you're not familiar with them. So when you're given a word problem, you will probably be given a mixture of units and have to do the unit conversion yourself. So you will get quite good at them. Then the last thing is determining, or the second to last thing is determining the reasonability of answers. Okay, so if you get an answer, you're going to do all this math that theoretically we're going to be good at, and you're going to get an answer at the end. And it's very important that you look at that answer when you're done and say, is this answer reasonable? If we're calculating a flame temperature, let's say, and we get a negative number, is that a reasonable answer? Probably not. We don't really get negative flame temperatures because that would be really cold. But if you use the equation and I had a student once give me a negative answer, and I was like, well, why would this ever happen in real life? And they were like, but that's what the equation said. And well, the equation is only useful if you do it right. All right, so everything we learn in this course is going to be a tool. This is going to be a tool in your toolbox. So if you have a hammer, you want to use the hammer correctly. Okay, so a hammer is really good for putting in nails. A hammer is not really good for taking out fillings. So don't use the tools for the wrong job. And then the concept of working together is very important. So if you have, rarely in real life will you do a job or do an analysis completely by yourself. You don't work in a bubble. So we want to get practice with working with other people. And obviously we have this online course, so we have the ability to have people from different countries or different locations work together. So you're going to have to deal with different time zones and different sleep schedules and different backgrounds and get the job done. So it's a very good practice to get used to in this global economy that we're working in these days. All right. So study groups are a good idea. A major benefit of education is the relationships you form, which is one of the downsides of an online education is you don't sit in a class with people for hours and hours and build a relationship with them. So we're going to have to do a little bit of extra work to get the relationship between students since you're so far away, but we're going to try and do that. That way when you get out of school and you have some problem that you can't remember how to do, you're going to be like, man, there was this student in the class who was really good at this concept. Let me call them up and they'll help me out. To this day, I still call people from my undergrad to help me out with things if I don't remember how to do them. All right, so we want to form study groups or at least make friends with the people in the class. The only time this isn't acceptable is during the quizzes or tests. And right now we only have one midterm. The midterm is basically just to make sure you understand the fundamental concepts in the course. and will thus understand the words that are coming out of my mouth for the second half of the class. So that's important. And so the relationships you form will help you throughout your career. All right, so the idea of this ties into the idea of knowing where to get information is sometimes more important than having information. In other words, you can memorize everything in the world, but if you can't use it, what's the point? So knowing where to find the information is much more efficient than trying to memorize it all. Yeah, okay. Grading scheme. When we have these problems, we're going to have these word problems. And so the answer is important, but the solution method is almost as important as the answer. So they're going to be graded in this way. You're going to have 20% if you use the correct solution method. That's 20%. All right, if you use the correct input parameters, you're going to get 20%. If you do the correct math, you may have to manipulate the equations you're using or something else. If you do the correct math, you get 20%. Use the correct units, 20%. So if you get the right answer, but if you write down the wrong units, you're going to lose 20%. And then 20% is going to be the justification of why your answer is correct. If you're calculating, let's say, a water temperature, and you're looking for the water temperature, the fire raised the water temperature in pipes to something because of some reason, all right? And so you know that the freezing temperature of water is 0 Celsius and the boiling temperature is 100 Celsius, so if you're somewhere in between there, your answer is probably reasonable. So you're going to put in these set points where you know information about the Newtonian universe, and you will write down, I think this answer is reasonable because it is between these points and these points where I know it should be. So you're going to use your professional judgment. And if you don't show any work, I can't help you. So basically, if you get the right answer, you're going to get 20% of the problem correct, because I'm grading based on this 5-point scale. So if you don't show any work and you don't justify it, what do you want from me? I'm telling you how I'm going to grade right now. All right, so we have a syllabus. We should talk about the syllabus. Take a little drink. All right, so here's the syllabus. It is available on Blackboard. Here's my contact information if you want to contact me. My email is just my name at eku.edu with a dot between the two words. We have a course description here. I'll let you read it to yourself because I do not like to read slides to people. And I assume you're fully capable of reading that. All right, so we have 3 prerequisites. Chemistry 101, FSE 120, our Fire Behavior and Combustion course, or equivalent, and Math 107 or higher. So we will be doing some math, and you'll be expected to know it already. We have 5 course objectives, if I count those correctly. Define and use advanced terms and concepts associated with chemistry and the dynamics of fire. Define and describe the development of fire in a compartment. So these will be the 2, let's say, objectives that are measured by the midterm. So this is a ABED requirement. When we do our ABED certification, we have to measure and quantitatively assess how we're meeting our objectives. So for these first 2 requirements, the midterm is going to be used. For the second 3, introduce fire-related measurement techniques, quantify and analyze fire dynamic phenomenon, including compartment fire behavior, and utilize current modeling programs to plot the growth of fire in a compartment. These will be your final projects. So we'll have a group final project. It's going to cover these 3 learning objectives, course objectives, and that way we will cover the 5 course objectives in the syllabus and be able to get our ABED accreditation. So the text for the course is Fire Dynamics by Gorbit and Farr, and I said we are currently writing the 2nd edition. We're using the 1st edition here, and so they've asked me to be a 3rd author, which I'm pretty excited about, to tell you the truth. And so that'll probably come out in 2014, and we will redo this course when that comes out, or modify it somewhat anyway. Okay, so we've got some supportive text. The only one we'll really use too much is this Fire Dynamic Tools User's Guide, because we will be using these. But I left these other texts in there because occasionally they come up and become useful, but I wouldn't recommend buying them. Okay, so we have a 16-week course. We have 16 weeks. The schedule is laid out here. And so for the first month, let's say month or 6 weeks, we are going to do one chapter a course, one chapter a class from the book. And in class 8, you'll have your first virtual lab. In class 14, you'll have your second one. In class 24, you'll have your third one. And in class 30, you'll have your fourth one. So to get to the virtual labs, I can't remember whether I included that in this lecture or not. You can go to Google and look up firesciencetools.com and click here. And if we go here, we have FSE 355 Virtual Laboratory. So we have Virtual Laboratory Exercise 1 through 4 listed here. And so you will have those to do. I may go into that in a little more detail. I can't remember. But you have the class topics listed here. All right. So you have a course methodology listed here. It's 100% online, etc. You can read all this. I do recommend reading all this for yourself so you know what's going on. You will, under course requirements, you will watch weekly lectures. Like we said, there's 2 of them. We'll complete weekly assignments. There'll be 2 of them. And you will complete a midterm exam and a final project. We'll have a virtual office. If you have specific questions, you can ask them there or on the discussion board. We have our grading methodology here. Grade breakdown for the course. We have participation. This is lecture notes, virtual laboratory exercises, going to be 20%. Homework is going to be 30%. Midterm exam is 20%, and the final project is 30%. So your grade is pretty straightforward. The grading scheme, in terms of A, B, C, D, and F, is normal. It's listed here. And you can calculate your grade using this straightforward equation. Rather than having a total number of points, like a lot of courses do here, we're just going to use this equation. That way we don't have to change the total number of points if we change the number of assignments. And so we're going to...
Hello.
Hey.
A package for $250.
I'll take it, but
Thanks.
I need to sign for it. They're out today.
Appreciate it.
Okay.
What's last name?
Rockwell? Me?
Thank you.
Yeah, sure. All right. Sorry about that. I am in my office on a Monday, but it's a vacation day. So anyway, sorry for that interruption. I don't want to record the whole lecture again, so I'm just going to keep going. That's what I get for having my door unlocked. Anyway. Okay, so we're going to use this equation. Basically, you take your total number of points earned divided by the total number of points possible for participation, multiply that by 0.2 or 20%. Same thing for the homework, except you multiply it by 0.3 or 30%. And the same thing for the midterm and the project. All right, so we'll have your grades available on Blackboard. We're not going to accept late assignments, but there will be opportunity for extra credit. If I remember, I will describe that in this lecture. All right, so you need to submit a copy of your notes. Grading's on Blackboard. Final project we'll give description of in the middle of the semester. Important course dates are listed on Blackboard. It's actually a better list than is on this Word document. Academic honesty is available at this website, so go look at that if you have questions. And your ideas are welcome and encouraged. I just hope you'll be nice about them. That'd be appreciated. All right, we got an honor code. If you have disabilities that need to be taken care of, please let the instructors know. If that's me or someone else, we'll handle that as needed. All right, so this is where I say you can use a Mac if you want, but it will be a little more difficult. All right, so Dr. Overholt isn't actually a doctor yet, but he's working on it. And he says it'll be done in about 4 months, so I believe him. We worked in this together for a summer and then went to grad school for a couple of years together, so he's a very intelligent guy and seems to get things done in a remarkably quick amount of time. Anyway, going back to the lecture. All right, so that's the syllabus. Questions about grades or other private matters should be addressed to the instructor or the facilitator in an email. We want a written record of our communication. In other words, if you say you have a discrepancy with a grade and you, let's say, call us on the phone or something, we say we'll take care of that, and that doesn't get taken care of, and you come back and say, well, you said you were going to do it, we may or may not remember, and this way you have, as the student, have written documentation of the fact that the grade should have been changed and can go directly and say, look, here it is, you said you were going to change it, you didn't do it, so let's fix it, and stuff like that. So that's really for your benefit rather than ours. We're not trying to be a pain, we're just trying to keep everything documented. So now we want to talk about fire in the U.S. So we've covered the introduction of the course. Now I want to talk about why do we want to take the course? Why is fire in the U.S. a problem? So in 2005, there were 1.6 million fires reported. So we had a significant number of fires. Now if you don't live in the U.S., this is an online course, so you might be in a different country. Chances are your country has a lot of fires too. But since this university is located in the U.S., I'm going to stick with U.S. statistics for now. Also, those are the ones that I have based on this USFA government website. All right, so we had 3,600 deaths, a little over 3,600. We had 115 firefighter fatalities, and this is especially a big deal since a lot of us in this course and this department are firefighters. I'm not one, for the record. I am more of an academic than a firefighter, but I am slowly getting trained theoretically. They're getting me turnout gear as we speak. 18,000 estimated injuries and $10.7 billion in fire damage. So you might say this is a lot better. This 3,600 is a lot better than we were doing 20, 30 years ago in the 1970s. This report called America's Burning came out, and that's what really started the push to get smoke detectors in homes, which has made a significant impact on lowering the number of deaths. But we're still getting a lot of people dying and a lot of people getting hurt and a significant amount of damage. So 10.5 billion, 10.6 billion, that's a lot of damage. And the thing is, it's all preventable, or the significant portion of it is preventable. These are all accidental fires, or arson fires, but arson fires might not be preventable, but the majority of them are accidental fires. And so this has not only an impact on people's lives, but an economic impact. And these right now, we're having tough economic times, and I presume that this will last for at least several more years. Destruction of industrial facilities is a really big deal because you're not only doing damage to the environment and using up water and injuring people, but you're also causing loss of jobs, loss of productivity. There are certain facilities in the U.S. that we can't make anymore. There's large-scale industrial presses that are left over from World War II that if they burn down, we only have 2 or 3 of them in the country, and we can't make them anymore. So we want to protect them and make sure they don't burn. There's also these clean room facilities where it costs millions or billions of dollars to build them, and if there's a small fire, then you're damaging everything in them. Medical facilities, electronic facilities, and server rooms. So these server rooms, we're going to talk about the value of server rooms and why we need to use clean agents in them later in the course. But point is, the economic damage is also an important factor for why we study fire science above and beyond the life-saving aspect of it. So when we talk about why we do fire science, we say save lives and save property. So lives are obviously number one. We want to get people out of the building, and then if we can save the property, we want to try and do that because property is expensive and there's not an infinite amount of money in the world. All right, so we have an in-class activity. This is one of the in-class activities I was talking about. We have 5 minutes. I want 5 reasons from you why we should know or why we should study fire behavior and combustion. Write down 5 reasons and then post your 5 reasons to the discussion board. So you have 5 minutes. This clock's going to continue to run down. And I'm going to stop talking for a few minutes so my voice doesn't go away. I presume that you know how to get to Blackboard because you're watching this lecture. And if you couldn't get there, you wouldn't be able to access the lecture. So on the left side is if you scroll down or just look at the top, there's a tab for discussion board. I think I meant to show this, but I forgot. Let me see. Yeah, if I go here, and we go to Blackboard, down here, there's our discussion board here, so click there and there should be a spot to put whatever we're talking about today. I'm out of orange soda. All right, almost done. 5 minutes. Let my little clock run down. Why not? Alright, so hopefully you've got that posted to the discussion board. We want to talk about who studies fire science at EKU. We have fire suppression personnel, fire protection engineering and code enforcement personnel, fire investigation personnel. Apparently you have 3 kinds. I think there's occupational safety in there as well, but we'll go with these for now. Alright, for suppression forces, we want to reduce fatalities and injuries, protect firefighters, identify when to engage in operations and when to get out, increase understanding so correct actions are made for any given situation. For investigators, we want to understand how fuels contribute to chemical reaction, how intensity heat required to convert fuels to gases. The intensity of heat required to convert fuels to gases. Ventilation requirements are a big deal in investigation as they mess with your patterns. Ventilation required to provide oxygen and remove fire gases. And we also for investigation people, we want to get rid of using rules of thumb. So we have a significant number of rules of thumb that I'm not going to discuss in this slide. But we want to stop using them to define where our origin and cause comes from and use actual science and the scientific method. Alright, so for engineering people, we're going to do code development, performance-based design. So this code development, you got to understand, for our building code, our life safety code, our fire code, they're all written by people, right? People came up with these codes, and so they're people experienced in the fields that they work in, but they are just people who may or may not have a fundamental understanding of the sciences that their codes govern. So when this next generation comes, we want to make sure that they have a good fundamental understanding of why fire behaves the way it behaves. And this is especially important for performance-based designs, or people who are doing performance-based designs, because now you're not relying on this code that has at least an empirical history where you say, okay, this code has been used for the last 50 years, so it's doing a pretty good job protecting life and property. Now you're saying, okay, the code doesn't work for this specific building. I'm going to do an individual analysis of the fire hazard for the load and the occupancy that we're dealing with. So you need to understand how the fire is going to behave in the given situation if you're going to do that kind of analysis by yourself, or analyze the analysis that was done by somebody else if you're the authority having jurisdiction. So it becomes important to understand fire science even if you're not doing the analysis yourself. Maybe you're analyzing the analysis to make sure that it's valid before you sign off on it and let people build the building or move into the building or whatever. So fire is defined per NFPA as a rapid oxidation process, which is a chemical reaction resulting in the evolution of light and heat of varying intensities. All right, this is the only definition I'm going to ask that you learn for the entire course. I don't like memorizing things, but if you're ever in a Dalbert challenge, which is when you're an expert in court and someone says this person is not an expert, I want to challenge them, that's called a Dalbert challenge, then whoever your other side is brings you in and starts asking you questions. And so if they ask you what is fire, you need to be able to rattle off this answer without having to think about it, because you're sitting there in front of the jury and you want to build confidence in yourself. So you need to say, what is fire? It's a rapid oxidation process, which is a chemical reaction producing light and heat of varying intensities, resulting in evolution of heat and light of varying intensities, or something like that. Okay, I said I'm not very good at memorizing. I wasn't lying. So you get it close. It'll be on your midterm. I make the on-campus students write it from memory, which doesn't really work for you guys, but I'm going to trust that you're going to write it from memory and memorize it for yourself. All right, so this is NFP 921. So we're going to watch a video called Firepower. If you're not familiar with fire dynamics in buildings, this is a reasonable video to watch to do it. If you're not familiar with enclosure fire dynamics, it is not new. It was made quite a while ago. But while we watch it, it's 16 minutes long. While we watch it, I want you to write down 3 facts about fire mentioned by the narrator that you find interesting or didn't know. He rambles off a lot of interesting things as they go through. And I want you to post these facts that you come across to the discussion board. All right, come on. I want this one. Okay, so here we go.
You are about to see a fire, one that has been planned, a demonstration fire. An ashtray with a still smoldering cigarette is dumped into the wastebasket. 2 minutes, 8 seconds. The contents of the wastebasket are smoldering. 7 minutes, 3 seconds. The wastebasket is in flames. 9 minutes, 14 seconds. The room is an inferno. You are about to experience the power of fire.
No one likes to think that fire might destroy his home or his family, yet each year fire claims more than 5,000 lives and causes nearly $3 billion in damage to homes. In the next few minutes, you're going to see exactly what happens when this home is involved in a fire. You'll see how rapidly events can unfold, how overpowering and deadly smoke can be, the tremendous impact of fire. And you'll grow to understand the role smoke detectors and sprinkler systems can play in saving your life and your family. But most important, you'll see what action you can take to survive a fire in your own home.
The majority of fire deaths occur at home. The home in our demonstration is a 2-story frame dwelling.
Our fire begins here in the living room where most home fires start. Let's take a look around. This is a typical family room. Comfortable couch, easy chair, books and magazines, and of course the wastebasket, the source of our fire. Through this doorway, just a few feet away, is the kitchen. During the fire, this door will be closed. Next to the living room and kitchen, the dining room, the setting for family get-togethers and gatherings. The front hallway, sort of a catch-all for a busy family, and the only direct exit for someone who may be upstairs. Let's see what we have on the second floor. This is the upstairs hallway, and here's the master bedroom. It's a pleasant room with the usual collection of sentimental items and valuables like this jewelry box. During the fire, the door to the master bedroom will be closed. And over here is a guest room. It's also comfortably furnished. This room is directly above the living room, where our fire begins. This is the children's bedroom. Bunk beds, chests, table, clothes, and toys everywhere. Only one thing distinguishes this house from your home. We've installed test instruments. And as the fire progresses, they're going to measure exactly what's happening with air quality and temperature. Now we're ready to see just what firepower can do to a home. A carelessly discarded cigarette is the cause of this fire, but home fires can start many ways. Space heaters, wood stoves, faulty electrical equipment, and cooking, among others. In most fires, there is a longer period of time from the appearance of smoke to actual flames. Remember, what you will see and hear was filmed as it actually happened. "30 seconds from first flame, the sofa ignites. From this point, fire grows rapidly. If you discover a fire, leave immediately and call the fire department from a neighbor's house."
One minute, 4 seconds from first flame. Polyurethane cushioning from the couch starts to melt, spreading fire to the rug. Smoke begins to fill the room. One minute, 23 seconds. The stairway to upstairs still clear. Things look safe here in the kids' room, but downstairs the fire continues to accelerate. One minute, 35 seconds. The smoke layer in the living room descends rapidly. Gases flowing out of this room now exceed 190 degrees Fahrenheit. One minute, 47 seconds. Light smoke begins to move to the second floor. 1 minute, 50 seconds. The smoke detector at the foot of the stairs sounds an alarm, providing warning before exits are blocked. Take action immediately. Crawl low where the air is cleaner. 2 minutes, 30 seconds. The temperature above the couch is now 400 degrees Fahrenheit. That's over 200 degrees Celsius. 2 minutes, 48 seconds. Smoke pours into the dining room, now only 4 feet above the floor. Thick black smoke moves rapidly upstairs. 3 minutes, 3 seconds. Melted polyurethane burns under the couch. Suddenly, the lampshade ignites. The temperature 3 feet above the floor in this room is over 500 degrees Fahrenheit. No one could survive. 3 minutes, 20 seconds. The upstairs hall is beginning to fill with black acrid smoke, making escape more difficult. From the outside, there may be no evidence of the inferno inside. 3 minutes, 41 seconds. The energy in the room suddenly ignites everything. Within 1 minute, the temperature has risen to over 1,400 degrees. Flashover. The living room windows break out. The entire room fills with flames, forcing huge amounts of smoke and toxic gases throughout the house. Only 2 minutes after the smoke detector sounded, the lower hallway is dark and filled with smoke. The upstairs hall and stairs now impassable. A second escape route is your only way out. 4 minutes, 33 seconds. Only now are flames visible from outside the house. If this fire occurred at night when most fatal fires happen, this would be the first exterior evidence of fire in progress. Flames climb up the outside of the house, entering the guest room window. Fire grows so fast that the fire department may not be able to rescue anyone trapped inside. Firefighters wearing protective clothing enter to search the house and to combat the fire. They begin to control the fire, causing steam to pour out of the first floor. Reaching the second floor, firefighters break windows to release heat and vent smoke. They open walls to check for fire spread. Not all fires behave like this one. Some will move slower, some faster. But if a fire starts in your home, get out immediately and stay out. You have just seen the power of an uncontrolled fire. Would you recognize this? It's the living room. There's not even a faint reminder of the comfortable room we saw earlier. Nothing identifiable but the coils from this chair. It took just 4 minutes from the first flame in the wastebasket for the temperature in this room to reach over 1,000 degrees Fahrenheit. The fire ultimately became so hot, the window glass softened and flowed like taffy. The kitchen door, which we closed, initially acted as a barrier to the flames, but it was no match for the power of fire. Eventually, the flames burned through the top of the door, rolled across the kitchen ceiling, spread smoke and deadly gases, hindering firefighters in their attack from the back entrance. Here, the remains of the dining room, nearly everything destroyed. Only a few items remain intact, such as the china in this cupboard. In the front hallway, flames also rolled along the ceiling, charring the upper portions of the room and the banister. Closer to the floor, there was less flame. But the smoke and intense heat still did a great deal of damage. Remember this? The telephone? And this? The big wheel. And here's the smoke detector that sounded our first alarm. Meeting no opposition, smoke, heat, and fire gases traveled to the second floor, searing and blistering everything within 6 minutes, cutting off the stairway as the family's main exit. Although flames never reached this upstairs hallway, it became hot enough to melt these plastic items. The bathroom, more smoke and heat damage. The children's room was directly in the path of the heat and the smoke. Look at the blistering on the bunk bed and these melted toys. Just 5 minutes after the first flame, a few breaths in this room would have been lethal. Just 5 minutes. In the guest room, flames from the living room came in through the windows and up through the walls. In their efforts to control the fire, firefighters had to rip down much of the paneling. Everything upstairs, damaged or destroyed. Well, almost everything. In this particular fire, this closed door is all it took to ward off smoke and hot gases from the master bedroom. While the temperature in the upstairs hallway was over 300 degrees, the temperature in this room never went over 77 degrees, and the valuable photographs and jewelry are undamaged. But remember, this may not always be the case. A closed door will give you the advantage of time to try a second way out, but it's no guarantee of permanent safety. When a fire starts, leave your valuables and concentrate only on immediate escape. No possessions are worth your life. You have just experienced the damage that fire can do to a home. And you've seen how smoke detectors, closed doors, and escape plans can lessen the danger to you and your family. Are there other measures we can take to lessen the danger and damage? There are. Let's turn back the clock. This is part of a residential sprinkler system, a device designed to spray water during the early stages of fire development. Watch what happens now. A fire identical to the one you just saw has been started in this room. Sprinkler systems have long been used very successfully in commercial buildings to control fires, minimize damage, and save lives. They have now been adapted for home use. In a typical residential sprinkler installation, sprinklers would be placed throughout the house. Triggered by heat, only those located near the fire will discharge water. As before, The fire grows rapidly. Smoke fills the room from the ceiling down. Only 2 minutes 11 seconds from first flame, the sprinkler controls the fire before conditions throughout the house become life-threatening. Of course, the room is very wet, but the sprinkler has confined the fire's damage to one small area. And so, for less than the cost of the furniture in this room, lives and property have been saved. Smoke detectors and sprinkler systems buy time in the race against fire. But no matter what precautions you take, no matter how small a fire may appear, its progress is rapid, its power awesome. Escape must be your top priority. All the firefighters in the world cannot alter those few critical moments between the beginning of the fire and the time when escape becomes impossible. What happens in that time depends on you.
All right, so I hope you found that useful and informative. So if you have any questions about today's class, please post them to Blackboard. That way, if you have questions, other people in the class probably have the same question. Go over the syllabus and answer the short homework. The short homework is on Blackboard as well. And take a look at firesciencetools.com. That is where your virtual laboratories are. It's the website I built when I was in graduate school and have been adding to it since I became a professor. So, I hope you